My name is James Kelly, and this is my overview of Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab is to use a bar magnet to create a magnetic field and observe the effects of this magnetic field using a magnetometer phone application. We will also observe changes in magnitude of the magnetic field based on the change in position of the bar magnet and eventually calculate the magnet dipole moment. The main physics principles for this lab are the Biot-Savart law, which gives the magnetic field based on the constant mu naught over 4 pi over 1 over r cubed, and then the cross product between the velocity and the r hat. Also, the distance dependence formula of a bar magnet, which is b bar equals kr to the n. Observations. During the experiment, when the bar magnet is very far away, the measured magnetic field in the x direction is nearly zero. But as the bar magnet is moved closer, the x component of the magnetometer increases. For the experimental model, it was found that n equals negative 2.6982, k equals 7.367 times 10 to the negative 7, and mu, the magnet dipole moment, is 3.684. The results of the computational model were 2.046 times 10 to the negative 5 versus 5.51 times 5.512 times 10 to the negative 5. Conditions of the experiment. The system is a smartphone which serves as an observation point, and the surroundings are the Earth and the bar magnet, which both produce magnetic fields. The initial conditions are a smartphone at rest, being affected by only Earth's magnetic field. It is assumed that the bar magnet is acting as a magnet dipole in order to apply the Biot-Savart law. Details of the experiment. The location of the magnetometer on the phone was set as perfectly aligned with Earth's magnetic field in order to minimize/eliminate its effect. Then, sliding a ruler perpendicularly both horizontally and vertically to the phone, and placing the bar magnet at the end, ensured that the position of the phone relative to the magnet was in perfect line with the parallel axis of the magnet. Then, various distances on the parallel axis were tested to find the correct magnetic field magnitude that the experiment called for. These values were then linearized by taking the natural log of each side and then graphed. Then, similar procedures took place in order to find the off-axis magnetic field. Here's the data from the experimental model, showing the linearization of the data, as well as on the top left, the parallel axis distances required to find magnetic field of the magnitudes requested, as well as on the bottom, the off-axis field data. The main results is that the distance was 2.62100914, and the magnitude of the magnet was 5.51246 times 10 to the negative 5. Calculations. In order to find mu, we need to first apply the distance dependence equation by looking at the linearization of our data to find n, which is just the slope of our linearized model, and then applying this into the equation when r equals 1 meter gets us that k equals 7.367 times 10 to the negative 7. Then, using Biot-Savart to find mu, you can find that mu equals 3.684 amperes meters squared. Computational model. The computational model was created using a Python code which calculates the magnetic field according to the manually calculated magnet dipole moment, mu. It picks countless observation points around the bar magnet and calculates and visualizes the magnetic field at each location. So going through the code, it starts by setting up some constants as well as importing our magnitude of magnetic moment, which is calculated from the previous part. Also creates a function to calculate the dipole magnetic field. And then on the right here, it sets up the distance as well as the various directions, axes, and magnet dipole moments used for the different observation points. On the right here, you can see the visualization of the magnetic field due to the magnet bar, or the magnet dipole in the code. The GLOSAP code showed a difference between magnitudes in the off-axis field, which was 2.046 times 10 to the negative 5 versus 5.512 times 10 to the negative 5. This difference points to the fact that assuming the bar magnet is like a magnetic dipole in the magnetic field it produces is not entirely accurate. Discussion. Choice of model. The assumption that the bar magnet would act as a magnetic dipole is likely slightly inaccurate, as the observed magnetic field of a bar magnet and the magnet dipole are very similar, yet experimentally and computationally different magnitudes of off-axis fields were found. Source of error. One key source of error is the fact that the magnetometer may not have been precise, with its margin of error being completely unknown. Further, if the phone was not perfectly aligned with the Earth's magnetic field, it would produce inaccurate results. It is essentially impossible to get the phone perfectly aligned. Conclusions. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meteor stick in some intermediate angle with respect to Earth's magnetic field? The results would not be at all accurate. The direction of the magnetic field would be completely skewed towards Earth's magnetic field because it is much stronger than that of the bar magnet. Furthermore, if two identical magnets were stuck together, then I would expect the measurements to be exactly twice as large because the identical magnets will combine their magnetic fields.